very useful sort, Quicksort. All right. And we applied divide and conquer approach. Yeah. But this time when we apply divide and conquer, so we will use a very different consideration. Yeah. All right. D.1, introduction to Quicksort. All right. Yeah. Why? Yeah, because when we study a new sort, we need to think about why we need to study a new sort, right? What's the point? Yeah. Emphasize overall performance. Yeah. So we need some sort with the best overall performance. So what is the overall performance? Average case efficiency. If a sort has the best average case efficiency, so that one, we can say it has the best overall performance. Right. So how to get that? So we need a completely different understanding of the sort problem. Our old sort problem, but this time we need to use a very different view on it to understand it. Yeah. All right. Divide and conquer. Yeah. We apply divide and conquer on the merge sort. Yeah. Now we want to compare it with the merge sort. Yeah. All right. The goal, make the overall performance as fast as possible. But the question is, it is pretty hard to control the overall performance, right? Yeah. Yeah. How do you control the overall performance? Yeah. 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 All right. Yeah. In order to get the best possible overall performance, you may need to sacrifice somewhere. Yeah. You cannot get everything. You cannot get a sort that is the best in every aspect. Yeah. For some aspects, this new sort may not be very good. Yeah. Here, we have to tolerate poor worst case performance. Yeah. Yeah. For the merge sort, we want to avoid poor worst case efficiency, right? Yeah. So you can see, comparing with the merge sort. Merge sort, we want to avoid that kind of bottleneck. Poor worst case, we treat it as a bottleneck, right? In our problem solving, because the efficiency, asymptotic notation, big theta of n squared, right? Big theta of n squared. That's very slow. That's the bottleneck. Yeah. So the worst case, we avoid this. But for the Quicksort, if you want to emphasize this overall performance, you have to sacrifice somewhere else, right? Yeah, so we have to sacrifice regarding the worst case performance. Yeah. All right. The probability for the worst case is very low. Yeah. 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 It can occur, but we want to control, we want to, so we may need to do something special, to make it, to make the probability very low. Yeah. Yeah. So at the end, we will talk about those ideas. At the end of this, in the summary part, we will talk about how do we do something special to make sure the worst case, the probability for the worst case can be controlled in the very low case, situation. Yeah. All right. Now we need to change the view on divide and conquer. Yeah. So let's do some comparison here. Compare it with a merge sort. Yeah. All right. So for a merge sort, you can see the divide step very fast, right? Yeah. So we just split our data right in the middle. That's our divide step. So here we use big theta of 1 to represent how fast is the divide step. All right. Conquer, we do the recursion. Yeah. So you do not need to really do anything special. Just automatic. Do recursion. Automatic way. Okay? All right. But the combined step, you need to do a lot of work at the combined. Yeah. So our merge step, in our merge step, we need to do our main work here. That's big theta of k. Yeah. K means the size of the data when we do the merge operation. All right. Yeah. But for the Quicksort, we need a completely different idea. In order to get something different, we have to make our main steps different. Right? Main steps different. So here are the main steps. Yeah, because conquer automatic, right? So we ignore the conquer step. Then the two steps, divide step and the combine step. These two steps, we want to do these two steps completely different from those of the merge sort. Okay? All right. So here, yeah, how can you make different? So you can see just the opposite way. Yeah. We put our main work at the divide step. Yeah. So we need to really do some important data division consideration in order to get good property. So why you do a lot of work in the device? Because we want our data after division, it should have some nice property. Yeah, because we want to get some nice property for our data. So we need to do more work to get that property, important property. Okay? All right. Yeah. So there, at the combined step, then we can take advantage of that nice property. With that special property, we can combine our data with the minimum cost. Big theta of 1, that's the minimum cost, right? Yeah. Yeah. So that's our new idea. Completely different from the old idea. Yeah. So then we can expect different result. Yeah. All right. Then, next, details. Yeah. We want to see what details we need to do in these two steps. All right. Now, how to make combined step easy? Yeah. We need to, do some analysis, important analysis work, because that is the goal, right? Make the combined step easy. This is our goal. Yeah. So when we start, we want to start from this point. Understand our data. What special property we need when we combine them? We do not need to do anything. We just put them together. That's the easiest way, right? Yeah. Put them together. There, it's done. Yeah. So that's what we want to have. Yeah. So we want to understand that data. Almost do nothing in the combined step. Okay? Yeah. Yeah. Put them together, then you're done. That's what we want. Okay? All right. But how can that happen? Right? Think about how can that happen? You have A subarray, you have B subarray. Okay? Yeah. After device step, right? After device step, you have A subarray and a B subarray. Okay? Yeah. Then after conquer step, you get A subarray sorted. You get a B subarray sorted. Yeah, conquer step. Yeah. Then, now we look at the combine step. What kind of special property do we need? Then, after we put them together, the whole array sorted, right? Yeah. So, all right. That's the property we want to discover. Yeah. Here, okay? Before conquer, not ordered, all right? Yeah. All right. After conquer, sorted. All right. Now, put them together. Yeah. All right. When we put them together, how can you guarantee? Yeah. Because after we put them together, we do not want to do any more work. Okay? We don't want to do any more work to make adjustment, make further adjustment. Yeah. All right? Yeah. So for that situation, yeah. For that situation, how can that happen? Okay? Yeah. So the whole array is automatically sorted. Yeah. When we just do the concatenation, right? So that whole array sorted. Yeah. How can that happen? So we need to, yeah. We can make assumption here. Yeah. Under what assumption this situation could happen? All right? Yeah. All right. Yeah. So when combine do nothing, yeah, our goal. So what condition do we need before conquer? Yeah, because if you want to make assumption on your data to have some nice property, you need to have it before conquer, right? Yeah. Before conquer, that is, at a device step. At device step, your data already has that special property. Okay? Yeah. That means you need to do your device step carefully to get that special property. Okay? All right. Yeah. So the property is this simple. This inequality is the property. Yeah. Look at this inequality. A of I, yeah. Here I, arbitrary index in A subarray. So A of I element, the value of A of I is less than equal to B of J. So this is the key property we need. Key property. Yeah. So you can also understand in this way, the maximum value of the A subarray should be less than or equal to the minimum of the B subarray, right? Yeah. A sub I, can we pick the maximum of A subarray? Yeah. So that's one special case of A sub I, A of I. Right. Can we pick special element in B subarray? We pick the minimum of B subarray. Yeah. Yeah. So this tells us the values of all the elements in A subarray must be less than equal to any value of an element in the B subarray. Yeah. That's simple. Yeah. That's the key condition. And when we do the divide step, we need to make sure we have this property. Yeah. Because at divide step, we have some freedom. Yeah. So we have a lot of freedom to work on our data. Yeah. The goal is, this property is our goal. Okay? How can that happen? Yeah. That's the main step of this algorithm. Yeah. The main step is this divide step. Yeah. After we get that, after we get this property in our divide step there, we're almost done, right? Yeah, the whole sort algorithm almost there. Yeah. Yeah. All right. So let's look at this most important step, device step. All right. Requirement. Yeah. How to split the array into two subarrays, A subarray, B subarray, such that A of I less than or equal to B of J. All right. Yeah. Yeah. So yeah, definitely, we do not require these two subarrays are sorted. We cannot require that because sorting is too costly. Yeah. So we don't want to do too much work in the device step. Okay? Sorting part, we leave it to the conquer step. Okay? Yeah. So we don't worry about the all the information in these two subarrays. All right. Next, let's look at the implementation details for this device step. All right. Yeah. All right. D.2, partitioning in Quicksort. Yeah. So that's what we call partition step. Partitioning. Yeah, we do partitioning. All right. All right. Yeah. So implement the device step. Yeah. Here, we need fixing. Yeah. So we need to really understand our data more this time. All right. Yeah, this algorithm is very smart. Yeah, very smart. All right. Now let's represent our data in this way. Before the device step. So this is our data. Okay. All right. Yeah. So now the question: how to split? You have a lot of freedom, right? Yeah. You can split it in a lot of different ways. So you have freedom to do the split. Yeah. All right. So now you want to split in some way. Yeah. After the split, you get a little A subarray, little B subarray. Yeah. All right. And with this key property, inequality, this inequality, that's the key property we want to achieve in our device step. Yeah, all right. Yeah, so here, let's look at these two subarrays first. The data sizes of these two subarrays. Yeah, each subarray has a certain data size, right? Yeah. Here you can see we don't know the data sizes of these two subarrays. So it's uncertain. Some uncertainty regarding the sizes of these two subarrays. All right. How to make it certain? In problem solving, we deal with uncertainty, a lot of uncertainty in problem solving. Yeah. Yeah. All right. So now we need to find some important step to get around the obstacles caused by this uncertainty. Get around it. Yeah. So what's the special way to get around this uncertainty, this kind of uncertainty, right? Yeah. So the smart way is like that. We try to find a special element to separate two subarrays. Yeah. This is the key point. Yeah. A special element to separate. Special element somewhere inside the original array. Okay? Yeah. Some special element. Yeah. And we use this special element as a separator of these two subarrays. Yeah. This design idea. This is our design idea. Yeah. So now the question, how special, right? The special element. Yeah. what kind of special property do we need for this element? All right. Yeah, so this key property now we want to have. Yeah, so if this special element can separate two subarrays with this property, can you imagine it should have this in-place property, right? This special element should be in place in the original array. That property, yeah? Why in place? It's very easy, because at the left-hand side of this special element, yeah, all the data values must be less than or equal to the part of the data at the right-hand side of this element. Then this element must be in place, right? It cannot move to the right. It cannot move to the, left. It cannot move to the right. Yeah. If you move out of place, something must be wrong, right? Yeah. Yeah. So here you can see the key property for this special element should be, it must be in place. Yeah. All right. But the question is, how do you find some element in place? Right? How to find an element in place? Yeah. 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 Actually, yeah, if you connect this in place property or requirement to this inequality, then it's not that hard. You need to connect these two properties. Then it won't be very hard. Yeah. Okay? Yeah. All right. Next, so we want to working on the implementation details, but we need to have a little more understanding on these two subarrays before we can work on the implementation details. All right. Determine boundary of the two subarrays. Yeah. Yeah. All right. Yeah. So here, this special element, it plays a role as the boundary of the two subarrays. Okay? Yeah. Separator. Okay? Boundary. Separator. Yeah. That's the role of the special element. Yeah. Here we use notation P. Yeah. This P, yeah. Yeah. So we have a name for it, the pivot element. It's the pivot element. Yeah. All right. Yeah. So we need help from this pivot element. Yeah. Next question: how do you select pivot element? Yeah. Which element can be used as a pivot element? Yeah. The next question we need to answer. Yeah. All right. Yeah. Yeah. All right. But this pivot element has the property related to our key inequality. That is, all the values of a subarray must be less than or equal to that p value. Yeah, in place. It is in place. And all the a subarray values are at the left-hand side of p. That means we should have this inequality. Similarly, the B subarray located at the right-hand side of P, so we should have P less than or equal to all the values of B subarray. Yeah. Yeah. In this way, if we can find a P that satisfies these two inequalities, then get what we want, right? Yeah. Yeah. So we complete the partition step in this way. All right? Yeah. So next, we need to consider this pivot element, qualification for the pivot element, right? Yeah. So which element is used as the pivot? Yeah. The qualification. Yeah. Yeah. Any element has an equal role in the array, right? Yeah, because we're not given any value information. in the original data. We don't know any value information in the given data, right? Then any element has an equal probability to be, the value at the beginning, at the end, in the middle, in any position, any value has the equal probability to be there. Yeah? Yeah. All right. Then that means when we pick the pivot element, there is no reason to favor any particular element, right? Yeah. Is the first element has better chance to be the pivot, or the last element has the better chance to be the pivot? All of them have the same chance to be the pivot. Right? Yeah, yeah, because we don't have any information. Yeah. In this, based on that analysis, we can see, we can pick a random element to be the pivot, right? Yeah. Random selection. Any element is good for the pivot. Okay? Yeah. All right. But another consideration. Yeah. This random selection, when we do random selection here, we are talking about values, right? Data values. Regarding the data values, we do random selection. Okay? Yeah. 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 All right. But other than data values, we have other things to be considered, right? Yeah, not just data values. Data value is just the one aspect to be considered. But there are other things we also need to consider other than values. Yeah. So another important aspect to be considered, position. Position of the elements also important. Yeah. Yeah. So all the elements in the given data, they have different positions, right? Yeah. So we need to look at which element in a given array has the most convenient position. Yeah? Position-wise, they are different. If you look at the position, for convenience, they are different. Some elements have more convenient positions than other elements. It's different. So we want to pick the most convenient positions for the pivot element. Yeah. All right. So we need to do some more analysis on the position part. All right. Yeah. Look at it. So if we pick the position somewhere in the middle, what would happen? Yeah. Randomly select. Yeah. Suppose we want to pick this element as the pivot. Yeah. And we also use this position to store the pivot. Okay. What would happen? So you can see for this position, the first, because it is not in place, right? When you randomly select element in the original array, well, so that selection, in general, this element won't be in place. Okay? If it is not in place, then you have to do some work, okay, to make it in place, right? Yeah. So you have to do work, make it in place. All right. So when you do the work, you need to move elements around, right? Yeah. Yeah. You have to change the positions of the elements. And this element, you can see, it plays a role as a roadblock. When you move elements around in this array, from left to right, from right to left, it plays as a roadblock. Yeah. Because you always need to do an adjustment with respect to the position of this element. That's too much work. Right? So you don't like this situation. Yeah. So you want to use a location that you do not need to move elements around some particular element, right? Yeah. So you want to find a special position, much more convenient, so that won't block your movement, right? Yeah. So those elements never blocks any of the adjustment. Okay? Yeah. So there are two positions, two special positions. The first element and the last element. These two positions, so when you move elements, other than these two extremal positions, right? Other than these two extremal positions, when you move, you do not need to do any adjustment. Okay? Yeah. So this analysis tells us you should place your pivot element either in the first position or the last position. But they're symmetric, equivalent. So we only need to pick one of the two cases to hold our pivot element. Position point of view. All right. Yeah. All right. Yeah. And when we put the pivot element in one of the two end locations, we don't worry about the value of it. Whatever value it has, we leave it there. Because only after we complete an adjustment, data manipulations, only after we complete the data manipulations at the end, we put this pivot element in place as the last step of the partitioning. Before we complete the partitioning step, so we just leave the pivot element in one of the two extremal positions. All right. Yeah, so based on this understanding, you can see, now, so here let's use the last position to hold the pivot element. All right. Now, then, look at the typical partitioning step, typical partition step, all right? Yeah, we have A subarray at the left part of this array, B subarray at the right part, excluding the pivot element. All right. And A of I less than or equal to P, and P less than or equal to B of J. That's the data state, the state of the data after the partition step. Oh, all right. The next step, we want to make it happen, right? So here, we know our goal. This is our goal. Okay? This is our goal. Now we need to make it happen. How to get it? All right. So the next step, D.3, implementation in partitioning. All right. Straightforward implementation. So the first round, we just want to make it happen. All right. It may not be the best way. So when we start, we just want to see, just want to do something to see how much can we get. Okay? After that, then we need to improve. Yeah. Yeah. All right, so in the first round, let's do some relatively easier way for the implementation. So we use 2 auxiliary arrays to help us divide the data. 2 auxiliary arrays. Okay? Yeah. Yeah. All right. To store 2 subarrays. All right. Yeah. Then, so let's draw a diagram. Yeah. All right. All right. Yeah. First, yeah. So let's assume we just take the last element as the pivot element. Okay? Yeah. So the first step, last element as the pivot for convenience. Okay? We know equally well. Yeah. Yeah. Okay? Yeah. You know, probability-wise, the same. Yeah. The last one, anyone. Okay? All right. So we pick the last one as the pivot. Yeah. Then we need to work on the remaining elements other than P. Yeah. All right. We scan the array from left to right. Okay? All right. Every time when we get a new element in our processing, we will compare it with the P. Based on the comparison result, we will determine the A subarray and the B subarray. Yeah. Okay? Yeah. So let's look at this. When you pick an element from capital A array, if its value, the value of the current element is less than or equal to P, then we drop it in the A auxiliary subarray. Because here, we use first auxiliary array to store the elements of the A subarray. Yeah. So we just when we do scan, so here, the capital A subarray here, right? Capital A subarray. So every time we pick the current, so we use index variable, going from 0 through n minus 2, all right? Yeah. So, yeah. So we can, if A of I is greater than P, we drop it in the B auxiliary subarray, one by one, right? Yeah. Yeah. Now you can see in this way, after we scan the whole array other than P, except P, then we have both subarrays, right? A subarray, B subarray, satisfying the condition we need, right? Yeah. So you can see, so simple. Yeah. One scan, we can get the partition step done. Yeah. One step. Yeah. So simple. After that, so after we get these 2 subarrays, we can copy them back, right? Because they're auxiliary array, so temporary arrays, right? Yeah. So we need to, copy them back to the original capital A array. Yeah. And these 2 auxiliary can be reused, right? Yeah, recycled. Okay? Recycled, all right? Reused, recycled. Okay. All right. Yeah. That's our first try. Yeah. We get the job done. Yeah. We get what we need. Yeah. Yeah. But the question, after this first round, in our second round, because first try usually not the best solution. No. It may not give us the best solution. So in our second round, we want to improve. We want to make the whole device step more efficient. All right, so here, what's the problem here? Related to efficiency, related to the resource usage. Why this first method is not very good regarding the resource usage? What's the resource? Memory resource. Okay? Yeah. When we manipulate our data, we need to use memory resource, right? Yeah. Here, these two subarrays belong to the memory resource. This resource part, think about, we use this memory resource more than necessary. Now, we use too much resource. That's the main issue. Too much resource in this step. Now, if you use too much resource, then the impact, because your memory resource is limited, right? Yeah. On your computer, your memory resource is limited. If your algorithm use more than necessary resource, in other words, you waste your memory resource. Yeah? Because more than necessary. Okay? You waste your memory resource. As a result, your program will run slower and slower. Yeah? Because the operating system needs to manage the memory resource. If the memory resource is occupied, then the operating system needs to wait until the resource released, then it can use for other data processing, right? Then waiting time will be longer. Yeah? Waiting for memory resource to be released, then the OS can allocate the memory resource to other data. Okay? Yeah. So the basic understanding is if you use more than necessary memory resource, then your algorithm will be slowed down. Okay? Yeah. It becomes slower. Okay? Yeah. So now we want to improve with respect to memory resource usage. We want to improve it. Yeah. In other words, to make it simple, we want to eliminate these two auxiliary arrays. We do not use auxiliary. So we get a partition step without using these two auxiliary. Then we save a lot of memory resource. Yeah. So our second round, so we do not use auxiliary. So we do partitioning directly inside original array. Okay? Yeah. That it is a little challenging. Yeah, it is a little challenging, but not too hard, right? Not too hard. You can do it. Okay? Small technical problem you need to solve. But you can make it. Yeah. All right. Yeah. So let's look at the improvement step. All right. Yeah. Yeah. So here, regarding this. Yeah. All right. In our second round, now we want to consider a concept. Yeah. So extra. So here, this topic, control extra space used. Yeah. Yeah. So there is a concept related to this topic. Yeah. So let me explain this concept. All right. So first, what is the extra space? Right? Yeah. The extra space concept first. Yeah. All right. So when we work on our data, we always need a space. We always need a space to store input and output, right? Input and output. Yeah. data stored for input and output. Yeah. Yeah. So that part, yeah. So that's the normal part. Yeah. Normal space usage for all computing problems. Yeah. All right. But many times we need to use the space other than the input output, right? Yeah. So that part, yeah, we exclude storage space for input output, then that's the extra space. Yeah. All right. For that part, yeah. So there is a concept here. Yeah. Yeah. It's called in-place algorithms. Yeah, still this in-place, but this time we use it for algorithms. Okay? Yeah. All right. In place, but this time algorithm. Okay? This concept. All right. Yeah. The previous one we call in-place elements, right? Yeah. So that concept, you know the meaning, but here, this in-place algorithm, for algorithms, the meaning is different. So what's the meaning? The meaning is the extra space used for the in-place algorithms is in big theta of 1. Yeah. You can use extra space. But your extra space is controlled by certain constant. Certain constant, big theta of 1. Okay? If you can make your algorithm with this property, then we call your algorithm, it's an in-place algorithm. So you have an in-place algorithm. Okay? Yeah. So here, we have this concept. Yeah. All right. Now, this place we want to control our extra space in big theta of 1. Yeah. Yeah. All right. You need to use small amount of extra space. Yeah. All right. Yeah. How to do it? So let's look at the details, how to do it. All right. All right. Yeah. All right. So we divided the storage locations in the original array into a few regions. First, S region. Yeah. S refers to smaller than. Okay. Yeah. Smaller than P. All right. So S, smaller than P. All right. Then L region larger than P. Okay. Larger than P. L refers to. All right. These two regions. Then there is one region, U region, unprocessed. Yeah. Because the data has not been processed. Data in S region, after processing, we place the data in S region. Data in L region, after the processing, we put them in L region. But the remaining part of the data unprocessed. So we need to work on the U data inside the U region. Okay? So we have these three regions to organize our data. Yeah. Because we want to eliminate auxiliary array. So we need to use the storage locations in the original array efficiently. Yeah. So in a stingy way. Yeah. We cannot waste the precious space from the original data. All right. Then we can grow S region, grow L region, right? And shrink U region. Yeah, because we keep growing data in S region, keep growing data in L region, and we shrink the data in U region. Okay, all right, yeah. So in that way, so you can see, when we start, we set these two regions empty initially, empty. Okay, U region full. Okay, yeah, except the pivot element. Yeah, all the elements belong to the U region initially. Okay, all right, yeah. All right, so the growth and the U region, yeah, unprocessed, yeah, initially whole, yeah, but at the end, empty. Yeah. After the processing, the U region is empty. So then we complete the partition step. Yeah. Okay, all right. Yeah. That's the idea. Okay, yeah. So this is, that's diagram describes what we are going to do next. Yeah. All right. Next step, D.4, example for partitioning. Yeah. So when we do the partitioning, here I just want to use a simple example to go through all the details of the partition step. Yeah. So very straightforward. Yeah. We need a concrete example to see how to manipulate the data step by step. Yeah. All right. Let's look at a simple concrete example. Yeah. Look at this array. Yeah. Yeah. A simple example. Yeah. So based on the description of our implementation design. Yeah. So let's do one scan from beginning to end. Okay. All right. When we start, we make the last element 4 pivot. Okay. Yeah. All right. Whatever value is there, we take it. Yeah. Here, in this example, I pick 4. Somewhere in the middle. Yeah, it's a good one, but it could happen the smallest value 1 there, right? It could happen. Yeah. Later, when we talk about worst case efficiency, yeah, so we will look at the largest element or smallest element in the pivot position. Yeah, that could happen. That's why at the beginning I said this algorithm cannot avoid the poor worst case efficiency. It cannot. Yeah. Because if 1 is there or 8 is there, that's the very poor worst case situation. No, it cannot avoid. Okay? All right. Yeah. But for the general case, it's pretty good for the general case. All right. Let's start. Yeah. So we use different colors to represent different regions. U region, we use white color. Yeah. Unprocessed. Yeah. So U region. All right. Now, so let's do the, yeah. So here, we use 1 extra space because when we manipulate the positions of the elements, we need 1 extra space for swap operation. Yeah. So very little. Yeah. All right. Now, let's use the area here to run the partition step. All right. When we start initialization, S region empty, L region empty. Okay? The first comparison, the first element 2, we compare it with pivot element 4. The result is smaller than 4, so we put it in S region. Okay? Yeah. Add it in the S region. Step number 2, the next element. Yeah. So here we use yellow color. Yeah, represent. So there is 1 element in S region. The second element, 8 greater than 4. Yeah, that means we should place it in L region here we use green color to represent L region. So we grow these two regions. Next one, 7 greater than 4, so we should drop it in the L region. Yeah, see, color it green. grow the L region. Very simple, right? Yeah, so easy. Yeah. But the next one, element number 4, 1 is less than 4. We should place it in the S region. That means we should color it in yellow. But here you can see one thing that happens. This green region separates the two elements of yellow color. That's not good. We want the elements in yellow region occupy the locations in consecutive locations. Okay? Yeah. So we need to fix it. Here, there is a problem. We need to fix this, separation problem. All right? There is a simple way to fix it. Yeah, very simple way. Okay? One swap operation can help us fix it. If we do swap operation between element 8 and element 1, okay? Swap 8 and 1, yeah, using extra space. Okay? Yeah. We do the swap operation, then after the swap, you can see all the elements in S region occupy consecutive locations. No? So you can see that's the reason we need to use the extra space for swap operation. All right. Then 3 less than 4, we should place it in the S region, but we need another swap operation, right? Yeah. Yeah. All right. Yeah. Swap 7 and 3, so we can, arrange elements in these two regions gracefully, right? Yeah. All right. The last one, yeah, very easy. We put it in S region. Yeah. So you can see when we put element in L region. Yeah, L region, we do not need to swap, right? Yeah. But when we put elements in S region, yeah, S region, the first element you do not need to swap, right? Yeah. Yeah. The first one, if it's in S region, you don't need to swap. But after the first one, then the remaining elements you may need to swap. Yeah. The first one, actually, sometimes you need, if you have, before you get the first element in S region, you already have green element there, then you need a swap. Okay? Yeah. Yeah. Try to understand the details. Yeah, because in one of our homework question, yeah, I ask you to count the number of swaps. Count the number of swaps. Then you need to really consider the, location. Yeah. So, what time you need to do swap? Yeah. What time you do not need to do swap? Yeah. All right. Yeah. But the last step, don't forget, we need to put the pivot element in place. Okay? Yeah. So we need another swap to put the pivot element in place. So swap element 8 and element 4. Yeah. So we get the whole partitioning done. Yeah. Okay? Yeah. So that's what you see. Yeah. After we complete the partition step, that's what we have. Yeah. 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 So divide step is done. Yeah. Yeah. So then conquer. Yeah. Okay? Yeah. Yeah. All right. So you can see that's the whole quicksort. Divide, conquer, the quicksort, like this. Okay? Yeah. All right. All right, yeah. So next, yeah, we need to look at how to control S region, L region. Technically, yeah. So it's also pretty easy. Yeah. We use two indices to control these two regions. Yeah. All right. I index and the J index. No? Because you need to store the value of I and the value of J. So you need two extra space. You know. Yeah. So 1, 2, 3. Yeah. But still constant, right? Yeah, still constant. Yeah. All right. So for S region, you grow I value. Okay? Yeah. Yeah. All right. L region, yeah. So you need to, the position, the index values for L region from I plus 1 through J. Yeah. Position values. Okay? Oh, yeah. All right. Before final in-place step. Then, every time you add one element in S region, you just increment I value by 1, right? Yeah, increment I value. Yeah. And when you grow the L region, you increment J value and so on. Right? Yeah. 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 Grow S region, grow L region. Yeah. All right. Yeah. Yeah. When you swap two elements, right? When you swap elements, you also need to do adjustment, right? Yeah, yeah, yeah. But this kind of technical details, yeah, so everyone can handle easily. Yeah, yeah, yeah. You just follow the logic, yeah, so you can handle. Yeah. All right. Yeah. Then, D.5. We need to look at the worst case efficiency of Quicksort. Yeah. Yeah. Worst case, yeah, pretty bad, yeah, but yeah, so the good thing is the probability is very low. Yeah. All right. Study the worst case. Yeah. When the position is extremely unbalanced, yeah, so you happen to choose the minimum element or maximum element to be the pivot. Although we know the probability is very small, but that could happen. Yeah. So you need to consider the worst case. All right. One worst case is like this. Yeah. 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 So the yellow region and the P and the green region is empty. Yeah. So S region, yeah, occupy all the positions other than P. Yeah, that's one of the worst case. Yeah, all right, yeah. Another case, yeah, other than P, all the elements belong to the L region. Yeah, in green color. Yeah, all right, yeah, yeah. So these two possible worst cases for each partition step. Yeah. All right. Here you can see, yeah, for these two worst cases, we need to use n-1 comparisons. But after n-1 comparisons, you only reduce the data size by 1. You only reduce the data size by 1. So size reduction is very slow. Yeah. So that's why it is, very slow. The whole algorithm is slow. Yeah. Yeah. Equally bad, yeah, actually, if you look at the asymptotic notation, they are equally bad. But if you really compare in a lot of details, slightly different, yeah, because regarding the swap operation, it's different. Yeah. Some worst case, you need to use a little more swap operations, slightly different. Yeah. So you need to slightly different. Yeah. All right. Recurrence equation for the worst. Now, we need to look at how slow for the worst case. Yeah. So we need to look at the recurrence relation, the running time complexity function. Yeah. All right. With T function represent total number of comparisons for the whole array. So T of n equals T of n minus 1 plus n plus 1. Yeah? The combined step, device step, we need to use n minus 1 comparisons. Yeah. All right? Yeah? But we only reduce the problem size by 1, so we need a T of n minus 1 for the number of comparisons. Yeah. All right? So this recurrence relation, you can see it's very easy. You do iterations, so you will get this 1/2 times n minus 1 comparisons. Yeah. 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 All right. That is big theta of n squared. So that is very slow. This device step, this worst case, the bottleneck. Yeah. So Quicksort cannot avoid the bottleneck situation. Big theta of n squared. Yeah. All right. All right. Yeah. So here, let me show you, some more cases about the worst case. Yeah. All right. Look at the data, this data. Okay? Yeah. Yeah. All right. This data, of the first partition, so we put the pivot element in place. Okay, the remaining, so you have so the remaining, so you have another worst case. See, because each partition spec you have a worst case, but after one partition, you have second partition, you get another worst case. See, then next partition you get another worst case. Because you put more elements, 2 elements in place. Then you need to do more partitioning. So more in place, but always worst case. See, each partition step you get a worst case. You get a worst case. Yeah, all right. Yeah. So at the end, you get it sorted, but this is the final worst case. Because all the way down from beginning to end, you always get a worst case. You can imagine how small is the probability. This could happen, right? This worst case could happen, but you can imagine how small is the probability. Okay? Yeah? So from beginning to end, all the steps, you get a worst case. How bad, how small is the probability?